Welcome, engineers, to a deep dive into one of the most fundamental operations in modern computing, the syscall instruction. Understanding how applications interact with the operating system kernel is crucial for building robust and secure software. It's not just about what your code does, but how it asks the system to do things on its behalf. Today, we'll demystify this critical bridge between user applications and the kernel's powerful capabilities. By the end of this lesson, you will be able to understand the fundamental purpose and role of the syscall instruction and operating systems, differentiate clearly between user mode and kernel mode, recognizing their security and privilege implications, trace the sequence of events from when a syscall instruction is executed in user space to its entry into the kernel, and finally, grasp the mechanisms by which the kernel safely exits and returns control to the calling user space application. Let's begin. At the heart of operating system security and stability lies the concept of privilege levels, primarily divided into user mode and kernel mode. Think of it like a strict bouncer at an exclusive club. User mode is where your everyday applications run. They have limited access, preventing them from directly manipulating critical hardware or memory locations. This isolation is a feature, not a limitation, as it protects the system from malicious or buggy software. Kernel mode, on the other hand, is the operating system's inner sanctum. It has full, unrestricted access to all hardware and memory. This is where the OS performs vital tasks like managing processes, memory, and I/O operations. When your application needs to do something privileged, like reading a file from disk or allocating more memory, it can't just do it itself. It needs to ask the kernel for help, and that's precisely where the syscall instruction comes in. It's the secure, controlled gateway to the kernel's power. So, how does an application safely cross that privilege boundary from user mode to kernel mode? The answer lies in the syscall instruction itself. When an application needs a kernel service, it first prepares its arguments by placing them in specific CPU registers. These arguments tell the kernel what service is requested. For example, read a file or write data. Then, the application executes the syscall instruction. This isn't just a regular jump, it's a special processor instruction that triggers a controlled transfer of control. The CPU immediately switches from user mode to kernel mode, often saving critical user mode context like the program counter and register states onto the kernel stack. This transition isn't arbitrary. The syscall instruction typically vectors to a predefined entry point in the kernel, often handled by a small piece of assembly code that acts as the initial syscall handler. This handler then examines the requested service ID and dispatches the call to the appropriate kernel function. It's a precise, orchestrated handoff. Once inside the kernel, the real work begins. The kernel's syscall handler, having received the request and its arguments, now invokes the specific kernel function responsible for that service. For example, if the application requested to read a file, the kernel's file system code would take over, interacting with device drivers to fetch data from the disk. This is where the kernel's privileged access truly shines, performing operations that user applications are restricted from doing directly. During this time, the calling application's execution is typically paused. The kernel might even schedule other processes to run if the requested service involves waiting for I/O. This is a fundamental aspect of multitasking operating systems. The kernel diligently performs its task, ensuring data integrity and system stability. It's a complex dance of data manipulation, resource allocation, and often sophisticated error handling. Once the service is complete, the kernel prepares for its exit, gathering any return values or status codes that the user application needs. After the kernel has successfully processed the syscall request, it's time to return control and any results back to the user application. This exit process is just as critical and carefully orchestrated as the entry. The kernel first restores the user mode context that was saved during the syscall entry. Things like the program counter, stack pointer, and general purpose registers.
It then uses a special instruction, often sysret or iret, depending on the architecture, to switch the CPU back from kernel mode to user mode. This instruction is designed to atomically restore the user's state and switch privilege levels, preventing any security vulnerabilities during the transition. Once back in user mode, the application resumes execution from the instruction immediately following the original syscall. It can then retrieve the return values from the designated registers, indicating the success or failure of the kernel operation. This complete cycle, from user mode through the kernel and back to your application, is the foundation of how applications leverage the operating system's capabilities. So, to recap, we've dissected the entire journey of a syscall. You now understand the privilege divide, the entry mechanism, kernel processing, and the safe exit back to your application. To test your understanding, consider: why is it essential for the CPU to save and restore the user mode context during a syscall?